Good day everyone. Our project is about effect of electrode type and welding current on fillet weld strength or TVE practical study. Session 1. Scenario and problem framing. A vocational school welding workshop aims to identify which electrode type and welding current produce the best fillet weld tensile strength while maintaining acceptable welding speed for student training. The experiment will compare three electrode types: E7014, E6013, E7018, and two current levels. Low is equals to 90A and high is 110A. Results will guide instructors in choosing electrode and machine setting for safer, stronger student welds. Problem A. CRD Completely Randomized Design. Title: Effect of Electrode Type on Fillet Weld Strength or CRD. Objective: compare average weld tensile strength across three electrode types. Factor: treatment. Electrode type is E7014, E6013, E7018 or nominal. Response variable: weld strength and continuous newtons. Design notes is 25 observation total. Randomly assign sample to electrodes, 8 to 9 per electrode. Data record per row. Sample ID, welder ID, electrode, current A, speed, cm mean, weld strength N. Problem B. RCBD or Randomized Complete Block Design. Title: Effect of Electrode Type on Weld Strength Blocking by Welder. Objective: compare electrodes while controlling for difference between welders or blocks. Treatments: electrode type E7014, E6013, E7018. Blocks: welder ID W1 minus W5. Response variable: weld strength N. Design notes: each blocks includes all treatments. Total 25 observation, blocks and reps arranged to approximate 25. Problem C. Factorial. Title: Interaction of electrode type and welding current on weld strength. Factors: A. Electrode type 3 levels: E7014, E6013, E7018. B. Welding current level 2 levels, low and high. Low is 90A and high is 110A. Response variable: weld strength N. Design notes: 6 cells. Replicate each cell 4 times equals 24 and 1 extra to get 25. Session 2. Hypothesis Development. For each frame problem, we give ANOVA type and correlation type. ANOVA type is a comparison hypothesis and correlation type relationship hypothesis. CRD electrode effect, one-way ANOVA. ANOVA hypothesis or comparison, HO microfarad E7014 equals microfarad E6013 equals microfarad E7018. No difference in mean weld strength across electrode types. HA. At least one electrode is different. Correlation hypothesis. Example relating continuous machine setting to strength. HO. Current A, weld strength N equals 0. No linear relationship between welding current and weld strength. HA, current A, weld strength N is not equal to 0. RCBD, electrode effect, controlling for welder. Two-factor layout but block as welder. ANOVA hypothesis or comparison, HO treatment, microfarad E7014 equals microfarad E6013 equals microfarad E7018, no treatment effect after blocking by welder. HA treatment, at least one electrode mean differs after accounting for welder. Block effect hypothesis example, HO block, all welder block means are equals, no welder skill effect. HA block, at least one block differs. Correlation hypothesis, HO speed, CM mean, weld strength and equals 0. HA speed, CM mean, weld strength and is not equal to 0. Factorial comparison hypothesis, HOA, no main effect of electrode. HOB, no main effect of current. HOAB, no interaction between electrode and current. Alternative hypotheses are that each HO is false. Correlation hypothesis, across fault dataset. HO, current A, weld strength N equals 0. HA, P, current A, weld strength N is not equal to 0. Session 3, data preparation. Here's how we organize our data in tables for Jamobi analysis. Each record shows the sample, welder ID, electrode use, current, speed, and resulting weld strength. Only the CRD sample table is shown below due to space, others follow the same layout. All 25 data points per design were entered into Jamobi with electrode and welder ID as nominal variables and current, speed, weld strength as continuous.
Question 4. Data analysis and interpretation, CRD, one-way ANOVA, factor electrode type, dependent Jamobi, output. Example, F222 equals to 15.47 minus P equals to 0.0001. Main strength, negative E6013 equals to 9075. N minus E7014 equals 3325. N minus E7018 equals 3890N. Interpretation. Since P is less than 0.05, there is a significant difference among electrode type. E7018 produce the strongest welds. Correlation. Current versus strength to R equals to 0.81. P is less than 0.01. Strong positive relationship. Correlation. Current versus strength to R equals to 0.77. P is less than 0.01. RCVD, two ways ANOVA. Factors, electrode treatment, welder's block. Jamobi output, example, electrode F times 220 equals 11.63. P equals to 0.001. Welder F, the quantity of force, and 20, it equals to 9.42. P equals to 0.002. Interpretation. Both electrode types and welder skill significantly affect weld strength. The E7018 electrode again produce the strongest result. Correlation. Speed versus strength. R equals to negative 0.45. P is less than 0.05. Faster speed, lower strength. Factorial. 3 times 2 ANOVA. Factors electrode types 3 levels. Current, low, high. Jamobi output, example, electrode F218 is equal to 20.72. P is less than 0.001. Current F1 18 equals to 14.63. P equals to 0.001. Interaction F218 equals to 6.84. P equals to 0.007. D. Reporting degrees of freedom and p-values. CRD ANOVA F222 here equals to 15.20. P is less than 0.001. This indicates electrode type significantly affect tensile strength. RCBD ANOVA treatment effects F218 equals to 8.4 T. P equals to 0.002. Treatment DF equals to 2. Residual DF equals to 18 after blocking. Factorial ANOVA electrode main effects F219 equals to 12.30 P is less than 0.01. Current main effect 1.19 equals to 9.10 P equals to 0.007. Interaction F219 equals to 4.60 P equals to 0.023. Practical TVE interpretation plain language. In simple terms, the electrode labeled E7018 produced the strongest welds on average. This means instructors who want stronger welds for training and assessment might prepare E7018 for student practice. Higher welding current 11 amperes tended to increase weld strength, especially when using E7018. However, higher current also shortens weld time and may require more skill to avoid burn through. So far, beginners use caution. Welding speed was negatively related to strength. Faster travel speed reduces tensile strength. Teach students to balance speed and control. Going too fast lower the quality and safety of the weld. Conclusion. The studies of electrode type and welding current significantly affect pellet weld tensile strength. E7018 with higher current produce the strongest weld. Welding speeds negatively affects strength. Session 5 Conclusion and insight. From our result, we learned that the E7018 electrode consistently produced the highest weld strength across all design. Current and speed are key factors. Higher current gives stronger welds while faster travel speed weakens them. Welder skill also affect the outcome, so training and consistent practice are important in TVE welding programs. In short, using E7018 electrodes at high current with moderate travel speed gives the best weld strength results, something our future TV. Recommendations. Practical TVE. Use E7018 for strength, critical student practice and evaluation. Train student to use higher current only after mastering manual control to avoid defects. Emphasize correct travel speed to balance penetrations and bed quality. Incorporate these findings into welding lab lesson plans and assessment rubrics.